Thanks for being here for the last talk, last day. Luca was worried about being between you and lunch. I'm between you and the pint, so try to make it worth your while. So my name is Eldad Kleiman. I'm a software engineering manager and engagement lead at Roche Information Solutions. And I'm going to be talking to you basically about how Roche, through its journey of digitalization, is leveraging open source mentality and developer communities in order to deal with the new types of algorithm developments for computer vision. Okay. So just kind of an overview about the organization I'm part of. So Roche Information Solutions is a kind of a new thing at Roche. It was founded a couple of years ago to be a software engineering-oriented organization within Roche to drive digital technology in a rapidly digitalizing healthcare market. Research decision support basically is a team inside Roche Information Solutions that develops internal research tools for our internal scientists and developers. And so the platforms and tools I'll be sharing with you today are not commercially available, but they're being used by a growing community of scientists and researchers inside the company. We're working with oncology datasets, which are largely computer vision datasets for digital pathology and radiology images. Although our platforms are focused on oncology, in the oncology disease area, they can also be extended basically to other disease areas that have imaging modalities. And lastly, the engagement team, which I lead, is basically responsible for the advanced users features and support. Advanced users is basically what we call our internal algorithm developers and coding and developing new algorithms. So, I've been lucky enough to join Roche at the relative beginning of its digitalization journey, about 10 years ago. And initially, what we did, we digitalized everything. So we got slides from microscopes, we scanned them, stored them on disk. We got different patient metadata, those were stored. So we were working basically with tens and hundreds of Excel sheets with file names and where those were stored and where they came from. And slowly, as developers and data scientists started using these data sets across the organization, collecting them and using them to develop new applications and algorithms, we saw a shift and kind of an evolution in data storage strategies. So from being data-oriented and files on disk and in folders, these data sets became cloud-based data lakes with APIs and graphic user interface that allows you to search and access and manage the data. Basically, concepts like FAIR were evolving for findability, accessibility, interoperability, and reuse of data. And really, it was pretty amazing to see this kind of evolution of data strategies. So the next step came with deep learning. So basically with the evolution and growth of GPU capabilities and a big buzz around deep learning, especially in computer vision with its success in ImageNet. And basically Roche identified the potential in this technology and started building compute capabilities inside the company. So we had several HPCs, so high performance compute clusters built inside the company, and those were available for our data scientists, for algorithm developers and researchers to use freely. And this led to a very, let's say, a broad experimentation in this field. We conducted myriads of experiments in fields like semantic segmentation. You've heard about some of this earlier today. We've done survival prediction, weakly supervised learning, style transfers, and so forth. And basically, this allowed us to also compete in different public challenges. and achieve a quite high ranking in those as well. So we organized the data, as you saw. We got our data lakes, we got the compute, we experimented a bit with the different use cases in deep learning, and what now? So I think we're entering sort of a consolidation stage in this area. In the last few years, we're trying to leverage the research that we've done in this field, in deep learning and computer vision, and to try to leverage it to bring more business value to our customers, to open up opportunities, and develop different, let's say, functionalities and products out of this. We're doing this in personalized healthcare by developing predictive algorithms for patient risk or mortality. We're doing this in companion diagnostics or in vitro diagnostics by developing algorithms that detect antigens for specific drugs. And we're doing this in reverse translation or drug discovery by developing explainable AI that basically allows us to understand the tumor microenvironment better and to inform back our discovery teams so that they can create better drugs and molecules. So in order to support this algorithm development internally, we're developing a platform that activates multimodal data, and users can basically use this platform to develop their algorithms and quickly pass them to the clinical infrastructures. And so basically what we're doing, we're helping data scientists and algorithm developers develop their algorithms and integrate them. So before I show you the actual platform itself, let's talk about a bit about these algorithms developers that we are supporting. So as I said, like we work with these algorithm developers to help them to develop their algorithms. And traditionally, these algorithm developers have been computer scientists, engineers that were very proficient in coding, in computer vision. They knew what Fourier transform was, they knew what feature engineering was. And this requires some sort of support and a specific type of support, right, to help these guys develop. And slowly, with the emergence of deep learning, we see more and more engineers and data scientists developing algorithms for computer vision, but they have no computer vision domain knowledge, because all a software developer needs today is to train a convolutional neural network, let's say, and train it with some annotated data, and they get a computer vision algorithm without needing to do any explicit feature engineering. And even more concerning than this is, like in the past, I guess, year or so, we have a new type of algorithm developer, and this is related to the buzz around one of my least favorite words, AI. So I realize maybe this is not the best place to say that with AI, but... And so just a quick detour to explain what I think might be one of the root causes that influence this change in the type of algorithm developer. So Polanyi's paradox is named after the British-Hungarian philosopher, Michael Polanyi, and it basically talks about how human knowledge of our own capabilities and actions are to a large extent beyond our explicit understanding. So like you can see, it's basically summarized in the sentence, we know more than you can tell. So this means that our tasks that we do, our mundane tasks, daily tasks, are mainly based on our intuitive, tacit knowledge, and we can't really verbalize them or explain how we do them. This is very common in many of the things that we do day to day, like driving a car or identifying somebody's face or lifting a glass of water, right? So it's very hard to explain in detail how to do that. And this is why, for many years, this has been recognized as one of the obstacles in the field of AI and automation, because in order to write an algorithm or a system that does something automatically, you need a very good description of how you perform the task. And this has all now basically changed, but this is still why we see mostly iRobot type robots and not C3PO housemaids. So I've mentioned this change, and this change with deep learning, basically, because deep learning completely sidesteps this whole paradox by helping us train algorithms without needing to explain to them what they should do. All we really need to do with deep learning is to give it annotated data, also basically data and labels, and recently not even labels. And this has even progressed with AutoML methods by allowing us to develop algorithms without coding at all, without even selecting a network architecture, without specifying hyperparameters or anything else, right? All we need is a ton of data. And this has changed dramatically, I think, in computer vision use cases for two main reasons. One is the exponential growth of the amount of data that we have, the imaging data coming from natural sources like cell phones, cameras, etc. And also in the medical field, from high-resolution CTs to digital pathology scanners. So we have basically trillions or more of data sets, of pixels that have a lot of, let's say, give us a lot of opportunity in this field of deep learning. Another thing is that these imaging data sets are typically annotated by very expensive experts. These annotations takes a lot of time, and it's also very inconsistent. So for example, recent studies show that pathologist concordance in annotations are less than 70%, and I've actually conducted experiments at Roche where pathologist concordance was less than 40% in cell classification. So this is a big problem. So essentially, we have our new algorithm developers now, who are these clinicians, biologists, pathologists, for example, that have been sitting on tons of annotated data that they themselves created. They've seen people like me, data scientists, engineers, use the data that they prepare in order to train these AI-based algorithms, right, machine learning algorithms, and they suddenly realize that they can do the same thing. Add to that the fact that in traditional pharma companies, there have always been more biological natural scientists and clinicians than data scientists. And this has always caused like long waiting times to get your data analyzed or to get your hypotheses tested. So basically, we're facing now an influx of new algorithm developers that don't know how to code. They don't know anything about computer vision. They barely know anything about deep learning. And what do they want to do? They want to develop computer vision algorithms with deep learning. And so this makes the work of supporting these algorithm developers much more challenging. And there is one silver lining about all of this thing, is the clinicians who are typically very conservative, they are willing to, because of this buzz around AI, they're willing to be, let's say, more welcoming of new algorithms now, especially if they're involved in the development of those. And this allows us to basically introduce also new technologies that we weren't able to do before, since they were considered experimental or science fiction. Yeah. So how do we, the engagement team, basically support these different types of algorithm developers? Our approach leverages these structured data lakes with graphic user interface that allows us to enable these non-coding developers to organize their data in different data sets, to filter out things. And then we have a self-serve paradigm with the internal open source libraries that our users can leverage in order to develop their specific algorithms. And basically, by delivering the correct tool to each person, to each user, we are minimizing the need for active support. Yeah. So the Iris framework is basically our data lake, but it's not only a data lake. It's a web-based platform which allows these users to design experiments, perform data curation activities, and basically develop and deploy their algorithms online. This platform was initially limited to digital pathology data, but because of the big popularity of its features and functionality, we are now expanding it to support also clinical imaging like CTs and PETs and other modalities as well. So the platform application is designed as a web portal, and this eliminates the need to install any software on the client computer. It also removes any dependency on the computer hardware or the operating systems. So once you're logged in to this platform, you can basically upload images, organize them into data sets according to your preferences, and copy images from one project to another in order to create basically the setup and the data sets that you need to train your algorithms. You can also create a team and share those data sets and projects with the different team members. So once data is organized in these projects and experiments, a user can view them in a dedicated web viewer. This viewer supports different types of manual annotations and visualization of algorithm results like masks or heat maps. The platform also contains an app catalog to which users can publish their applications in order to share them with the community. They can also trigger applications that they publish there on thousands of slides on our platform compute resources by a click of a button. So this makes basically the algorithms usable for the entire community and without needing to think about how or where to run and deploy them. So if you give a man a fish, he will be hungry tomorrow. But if you teach a man to fish, he will be richer forever. And with this proverb in mind, we're developing inner source libraries for our advanced user community. Developers are not only permitted to download and reuse the code, but they're encouraged to fork it, use it wherever they want, copy it, and basically take it away from us. We encourage them to contribute back to our source code and to our community. And the advantages of doing that are getting support basically from our team of experts, but also from the different community experts. This kind of community with the open source magnet at the center of it basically triggers a lot of collaboration between different departments, silo breaking, and is basically creating this community of experts that grows and supports itself. So we offer our customers basically two advanced user open source products. Pyris, which is a shallow-level Python API library that allows a user to connect to our platform and interact with the data on our Iris framework. You can basically use it to push and pull images, to post annotations on an image, or to upload or download analysis results for a specific image asset. The other open source library we offer is called Iris AI. It's basically a portfolio of deep learning-based modules for algorithm development. This was also initially only for pathology, but now we support different use cases and modalities like radiology and genomics. We have modules that are specifically designed for semantic segmentation, survival prediction, multimodal analysis, and others. So when I started developing Iris AI as a purely research tool in pharma, we were two users basically using this software. But in the last 2 years, as we open sourced it, the amount of advanced users using this product grew from 2 to 200. In comparison, our engagement team that supports these users grew just from 3 engineers to 6. So we basically spent the first year after open sourcing building tools and methods that will allow us to manage this growth and scale up. We have Slack channels on the community for the community to talk to each other and to receive support from our team. We have automatic documentation servers and a website with dedicated blogs that explain the different modules in the library. Each of these blogs contains a runnable Jupyter notebook that a user can basically download and run without having any prior knowledge of that specific technology. So for example, if a user doesn't know anything about transformers, he downloads the Jupyter notebook, he changes the data to point to his own data set, and he can basically run that transformer training without having any knowledge. So addressing a growing need in the community for quick and easy prototyping and reproducible pipelines, we're also starting to leverage Kubeflow in order to extend our platform and the services that we provide. We're doing this, first of all, with Kubeflow pipelines. Kubeflow pipelines is a module in Kubeflow that allows you to consistently and reproducibly run complex workflows of algorithms. So we have pipeline templates in Iris AI that provide an internal compute environment and allow users to trigger and manage their advanced analytics experiments. And since in Kubeflow pipelines are run with the graphic user interface, our non-coding users can also leverage this feature in order to trigger experiments and analysis on their datasets. These pipelines can also be systematically run at schedule in order to run existing algorithms and verify their results on new incoming datasets in order to see if there's any data drift. Another module that we're using in Kubeflow is Kubeflow Notebook Servers. Kubeflow Notebook Servers is a module that originally allowed a user to launch a Jupyter Notebook server on Kubeflow. In the last few years, this feature has evolved to support more and more functionality and run more software like VS Code, RStudio, and recently also customizable user software. So this enabled us to conceptualize what we call now Iris extensions. Iris extensions are basically interactive web applications that are connected to our platform via our API libraries like Pyris. And so they can be developed, uploaded, and triggered at will by any user. So one of the things that we notice is that with the influx of new users with new use cases, basically we had a lot of new user interface functionality requests. And these requests were flooding our engineering teams and creating long development queues. Iris extensions allows us to overcome these queues by allowing users to develop their own user interface by themselves and trigger that connected to our platform data on the Kubeflow framework. This allows us to eliminate these long queues and have better user satisfaction as well. Another advantage of this extension concept is that it allows us to quickly and efficiently connect third-party software to the data on our platforms as well. So one example of such extension is a Deep Pathology Studio. Deep Pathology is a company that actually emerged from Roche's own startup accelerator in Munich. They created a software that allows codeless development of digital pathology algorithm for different use cases like cell detection, segmentation, tile classification, and object detection. So this off-the-shelf web app has been integrated into Iris through the extension concept, and it allows our customers to create deep learning-based computer vision algorithms and deploy them on our app catalog without writing a single line of code. So all of the images and annotations that we generate using this third-party software are synchronized via Pyris with our platform data, so we remain with a single point of truth. And this collaboration with Deep Pathology and the concept of Iris extensions allowed us to complete this integration at a record-breaking time with almost no use of our internal engineering resources. So yeah, to summarize, deep learning has transformed the types of audience that wants to develop computer vision applications. finding ways to service and maintain this large influx of new developers with no software or computer vision domain knowledge is a big challenge for us. And creating open source communities and self-service solutions, it can mitigate the stress on the engineering teams and create a self-sustaining user ecosystem. And that's all I have, and thank you very much. Happy to answer any questions.
Thank you for the presentation. And I have one question, because talking about the medical images and open sourcing, a question comes to my mind, like, how are you dealing with data protection in that sense? What's the pipeline regarding that, or how do you deal with that?
So the question was, how are we dealing with data annotations?
With data protection.
Protection?
Yes.
Yeah, it's actually quite a complex issue. So this really depends on the geographies. So for example, we have data sets that aren't allowed to leave the EU. And for that reason, we have specific instances of our platform that are based in Frankfurt, and data must not leave that geography. For other data sets that are public, it's less of an issue. But this is something that we are forced basically to control. So when users upload data, we have a team that makes sure that no patient information can enter the system where it's not allowed.
A fascinating presentation, Eldad, and quite an achievement, I would say. I mean, to develop such a complicated system and get users onboarded. I have three questions that I'd like to ask. One is, I mean, you've described how you've created this whole self-serving community, but still there must be a learning curve, right? From somebody to go from zero to expert, right? So the first question is, you know, how have you managed that, right? The hand-holding in the beginning. Then the second question is, you said that you have these Jupyter notebooks people can run on their own with their data set, but you know, it's not necessary that their data is in the format that the Jupyter notebook would be ready to consume. So how does that kind of work? And the third question would be, what guardrails do you have in place to prevent them from nuking the whole kingdom? You know, running some errant program that takes the whole system down.
Okay. No, very good questions. I'll start with the first one. How do we still support the needed ramp-up of users? This is the work, basically. So, I mean, these whole systems and kind of methodology that I presented, it solves some of the problems. But of course, like we are busy more or less 24/7 supporting the rest. And one of the ways that one additional way that we mitigate this is for the different departments or groups that work with us. We try to find one developer that seems to have the most experience and knowledge, and he basically becomes this kind of a super user or a hero. And then he also helps support his own use case in the group. So this is one thing. The second thing, like what's nice about the community, because people request the support on this open Slack channel. So let's say there are 10 people requesting support at the same time. We're only 6 people, it takes time. But then other users, you know, chime in, because a lot of the problems are recurring. So a problem that a new user has is typically a problem that some experienced user already solved some weeks or months ago, and they chip in, and it's actually nice. Every time that I'm not fast enough to answer a user and somebody answers, it's actually telling me we're doing something right. And okay, the second question was about the Jupyter notebooks. How do we make sure that the data fits, right? So this is the advantage of having these open source libraries connected to our platform. So the platform is the single point of truth, and it holds all the data and annotations. These Jupyter notebooks, they don't work with files on disk. They work directly with the platform data through Pyrus. And so we basically lock that circle. So they have to get the data through Pyrus, and this is why they have to get the data in the expected format. And the same goes also to when they want to upload the data back. You can't just upload anything. You have to go through our APIs. And this is how they manage to also very easily upload those masks and heat maps from their trained algorithm back without needing to follow some specific instructions. I mean, there are always the special use cases, special users that need special attention, but this is covering like the 90% of the users. And the last question, a funny one, like how do we make sure they don't break the system? Well, this was a learning process for us, so I can't say that the platform didn't crash. I might have crashed it myself several times, download 10 billion tiles from 16 different machines at the same time, and yeah, you see some issues, and we've had users, let's say, test our limits from time to time. I mean, it's good. We have methods now that include both auto-scaling of different pods. So the platform is based on AWS. So for some of the modules, we have auto-scaling. Another thing that we do now is that we have a limit to the amount of users calls per second. And so the combination of these two, we're seeing these crashes less and less.
Thank you.
Okay, so thanks a lot, everyone.